just to continue on the topic of exceptions, so I just wanted to, before we go back to looking at the slides, just want to go over the idea of if you have some code running, code runs to a certain point, if you call a function, so this is just, I'm just talking about comparing exception handling to calling a function, because in some ways they're similar and then in some ways they're different. If you explicitly call a function, the function control goes to whatever your function is. Everything runs fine, we get to the bottom, and we return to here, and we just continue where we left off. So that's a typical function call, and we come back. Exception handling is a lot like a function is being called, except that it's not being done explicitly. However, we know that throwing exceptions, we can do it explicitly. But an event will occur that was unexpected. You divide it by 0, or you try to open a file that's not there, something like that happens. And so what will happen is, it will implicitly call a function. And that's what your exception handler is, it implicitly calls a function. So now, which one gets called? Since we're not calling anything by a name, we have to know where the code is to handle it. And there isn't one piece of exception handling code that handles every case. So we may have many different exception handlers. So we may have a piece of code here, a piece of code here, a piece of code here. And we have to figure out which one of these to call. So again, we're not calling anything by name, and yet there's many routines to call. So the way the exception handling is done is, an object is generated and sent somewhere. The object is passed somewhere, and then some evaluation based on the object determines which method gets called. So now the question is, there might be multiple methods to handle the same problem, and one of them might be based on the operating system or based on your choice, might determine which is the one that should be called. So the operating system builds a stack structure for you when your program starts running. And it might say, let's say, for example, we have a pointer to a routine called terminate, which is the operating system's kind of last resort. Anything that goes wrong, really can't figure out how to handle it, there'll be some code that runs there. Then the operating system could start stacking up other routines that reside in the operating system, and then if a certain problem comes, and the type of the object that gets created matches it, that routine will run. What you could then do, so before you get involved with your exception handling, with your try-catch statements, if your code is running and something unexpected happens, the way the processing works is the operating system creates an object on your behalf and basically sends it to this stack, hopping down the stack looking for object handlers of the same type. As soon as it finds something that matches that type, that's the routine that gets called. The other difference between calling a method or a function and having an exception handler get called is we don't come back to the place where we left off. We just run this routine. And then what happens after that, this could be the end, or we could ourselves catch this, like we've talked about, we can catch this and then pick up at a later place in our code where we left off. Then what you can do with your try and catch routines is you can add on top of the operating system stack. So you can start adding more routines on top of the stack. And the order of which, where the catch that is closest to your try block is the ones that are on the top of the stack. So if you run something, if you have now a try block, if you say try and then catch with a certain type of object, you're putting stuff, E1, E2, you're putting routines on top of the stack if something goes wrong. Now, if an exception happens in here, we will go, control will go to the stack looking for a match. So that's kind of where they get that expression, throwing an exception. We're throwing it to the exception stack. We go popping down the stack until we find an object that matches it, matches the type. That routine will then run. When processing is done, we come back to the end of your try and catch section, and we'll pop off any other routine that you had put on the stack in here. And then at that point, we would pick up where we left off. Also, within your try statement, you're allowed to throw your exception back at the stack, which means that a further one will run too. So I just want to do a little bit of the behind the scenes of what's going on. And that's kind of tough to do on a slide, so I'd rather do it on the blackboard. So then, okay. So now just picking up our discussion on exceptions, if we look at exceptions in destructors, now that we kind of know what exception handling does, what would happen here? If we had something that was, let's say for example, we were reading a book. So we have a page pointer, the page pointer reads a page from the book, performs some operation using this pointer, and then when it's done, we delete the pointer. Then we come up and read another page, we create another page pointer, read a page, get the page pointer, read a page, delete the pointer. Suppose we were doing this over and over again, right? Now suppose during read page, an exception occurs. What happens? Even if we wrote try with some catch down here, the exception handler starts running. If we come back here, if we did catch it, we would come back here, but we would not do the delete pointing, right? We would not delete the page that's being pointed to. That would get skipped over, right? So we would have kind of a memory leak. Well, I shouldn't say kind of. We'd have a memory leak, but you might think, well, this happens once in a while, but the way this code is written is we just keep reading pages out of a book. But suppose there was something wrong with the book and we kept hitting the same exception while we were reading the page. Then we'd have all these pages that we gathered and never freed up. So okay, so we were on this page, right? Yep, we were on this page. Okay, so a way around that using the try and catch would be to say try reading the page and then catch anything. And if we hit a problem, then in our catch statement we delete the page and then throw it back at the operating system. So this would make sure we delete the page, right? And then we have the delete in case nothing goes wrong. We want to still be able to do the delete at the end, right? Actually, maybe this delete should have been in the while, right, to match the last set of code. So it would be like this. So we put it over here. Okay. Okay, so this would be a solution to it, right? But then we'd have to put this in all over the place. Everywhere we have a pointer that's pointing at some big operation that has potential to break, to have an exception. And then we always have to say try and then catch it and then delete the pointer, the thing being pointed at by the object, just to make sure we don't have a memory leak. But this would work. So we'd have to put the code, put this try catch stuff all over our code. So one mechanism around this, which kind of came from exception handling, but it's just in general a thing that they decided to add to C++, is the idea of what's sometimes called a smart pointer or an auto pointer. So an auto pointer is a pointer that when the pointer goes away, when the pointer is being destroyed, it comes with a destructor that will also delete the thing it's pointing at before it goes away. So the idea is if we go to this previous code, I'm sorry, if we went 2 levels back, if this code ran, this line ran, then this line ran, and then right here an exception occurred, this would never run. This is where, we're not deleting the pointer, we're deleting the thing being pointed at by the pointer. That's what a delete does. The pointer will go away, the storage will be destroyed, but the thing being pointed at will not be destroyed. But if we created this as an auto pointer, an auto pointer has its destructor, so this is now a template, its destructor will say if the pointer is pointing at something, then delete the thing that's being pointed at before we destroy the pointer. So this now takes away, so wait, do you see an advantage and a disadvantage to this? This is basically saying we can declare anything of this pointer by doing something like this. So let me first use it in an example, and then we'll look at the code that's going on behind the scenes. So this is a solution to the problem before. We used to say we had a pointer, we'd read the book, I'm sorry, get a page from the book, then we'd start reading the page. And if an exception occurred, we couldn't do the delete. Now we're saying we're going to use this template, which C++ provides to us. It's an auto pointer, so it's an auto pointer pointing to a page instead of what it used to be, just a pointer to a page. And then we read the page. If something goes wrong, we don't delete what's being pointed at. I just made this comment now. But instead, when this pointer gets destroyed, the code for its destructor will say, if the pointer is pointing at something, then delete the thing that's being pointed at before we destroy it. This is just some other supporting code. We don't really have to go through it for tonight's purposes, but if we want to look at auto pointers closer, all they really are is normal pointers that have the operation. The most important operation is basically, it does some checking for you if the pointer's null, but the most important thing is that when it's being deleted, it will always delete the thing it's pointing at before it goes away. So is there an advantage and disadvantage to that?
Prevents memory leaks, but if you need it for something else, then you're kind of correct.
Well, it prevents memory leaks, I guess now, in really 2 cases. One is the exception case. When an exception comes, something happens unexpected to you. Also, in case you made a coding error, right, and forgot to delete the thing, this will delete it for you. But where's the case where you couldn't use this? Like if this was just a better solution than pointers, they would get rid of pointers and only use these. They wouldn't have.
When you needed your storage for something else, like
like
database query or something.
Right. If you have something, if you have 3 different pointers pointing at something, and one of those pointers goes away, you don't want the object going away. The other 2 are still working on it. So you should only use this in the case where you know once the pointer goes away, nobody else would ever want it. Then this thing helps. This is like a safe pointer. Whatever it's pointing to, there's no strange circumstance, either an exception or bad programming, that would cause the pointer to go away and the object to still be around. Okay, so then using the auto pointer, this ends up being a solution. So the change was delete this line and add auto here. And then we can be guaranteed that if an exception occurs during this processing, the page that we're pointing at will go away in addition to the pointer going away. Okay, so let's see, C++ also puts this guarantee in. when you go and call a delete of a pointer, if the pointer is currently pointing at 0, which I guess would be the beginning of the operating system, it's not going to try to start deleting the operating system. It'll just say, oh, it's 0, I'm not going to do anything. So you don't have to say, if pointer not null, then delete. Every time you go to do a delete, you could just do a delete and it's implied that that's going to happen. So then another interesting issue comes up. Suppose we had a class that had made 3 kind of big objects during its constructor. So in a constructor, let's say, because MyMovies is the class, and this is the MyMovies method, which means it's the constructor. Suppose we had 3 pointers. 3 pointers, and we do a new of some object. And so these are kind of vague concepts, but we go to create some popcorn object. So this is now the constructor of some type popcorn. That now runs. And we don't know what's going on there. There might be an exception that happens. But let's say this works successfully. We create popcorn. Now we go to create some big movie. That constructor is now running. Suppose an exception happens. In the middle of us constructing an object, what should happen? Should this object, let's see, if there's an exception thrown during the creation of a big movie, should the MyMovie object be destroyed? Should the entire destructor run? So the destructor of a movie would go and destroy the popcorn and the movie and the soda, right? It doesn't know that the object was partially created. It assumes it was fully created, right? So if halfway through a constructor an exception occurs, what should happen? Should this thing, as far as this object is concerned, should this be destroyed? Can you run it? So suppose the destructor gave a bunch of instructions on how to destroy all 3 of these things, but some of them are not even created. And now we start to destroy them. We start taking the values, and based on what their values are, we start making decisions about that. Would you, if you were designing the language, would you let a partially constructed object get destroyed?
Wouldn't you want to? So you'll free up space?
Well, if it was fully constructed, then we can fully destroy it.
Even though, if you, let's say, create the MyMovies object, you have to create a popcorn, and then if you have an error in the movie pointer, you already have the popcorn object created now. Don't you want to be able to delete that?
Right, so let's say we had an exception during making the movie. So really this object is really made up of 3 other objects, right? And let's say the first one is made, and then halfway through the second one we hit an exception. Should part of the exception handling goes and deletes anything that was completely created, completely constructed, but what should it do about something that was partially constructed?
Well, what's the point of the movie object without the movie?
Well, yeah, I guess what they were thinking was, if we have a destructor that says destroy this, then destroy this, then destroy this, it's going to start destroying things that were never created or partially created. And they're worried about hitting errors with that.
But why, if it's trying to delete, like say it's trying to delete soda, the soda doesn't exist, so how could it delete the soda when the soda never existed?
But we do have a pointer to what we thought would be soda. And then we could take that pointer and then start running operations on it. Or we might...
That's if we delete it or if we don't delete it, running the operations?
If we try to delete it. If we try to, so in a destructor, if we try to run operations on something that was partially or not created, is there a danger to that?
Well, in this case, wouldn't the, because it does it in reverse order, so wouldn't the movie pointer be that aired out, wouldn't that be the first destructor to run? And then popcorn, and then because they're their own objects, and the soda destructor never really run in this case?
Well, we could in our destructor code, we could start, so we basically have 3 pointers.
Yeah.
the order of the memory being deleted would go in reverse order
Yeah.
that they were constructed. But what we do in our destructor, we can kind of do whatever we want. We might take something from the soda and mix it with something from the popcorn and then take some actions, and the soda's not there, but the popcorn is. And our code is counting on it being there, which means we'll probably hit an exception too, because we're working with like half-baked storage. So what they decided to do was, if an object is partially created, they just don't destroy it. They let it be a memory leak, because of the danger of trying to destroy it. And I guess the hope is you don't have too many partially created objects. It's not like a common memory leak. It's not like you're in an infinite loop and you'll be doing this over and over. But then again, it could happen. You could go through a loop that's trying to make 10,000 movies, my movie objects, and it keeps hitting the exception in the same routine. Now you're going to have a lot of popcorn laying around, right? So,
Why couldn't you just write a destructor that just destroys everything and not really, what operation would you need to perform though on it if you're
Well, no,
just
but-
destroying it?
no, we can write a destructor that destroys everything, but you can't explicitly call the destructor. Destructors get called implicitly when the object goes away. You can't say, for this object, call its destructor, even though it's not destroyed yet. So, yeah, so what's unique about this is an exception occurred, and we're counting on an implicitly called routine to clean it up. And we don't know if that routine is going to be in trouble because it's trying to clean up something that's half-baked.
Okay, so
So-
the routine could get messed up because it's trying to mess with something that doesn't exist, and since it doesn't exist, you could start going haywire.
Right, and our destructor could read from popcorn and then try to read from soda, and based on the two things it read, make a decision, and then it gets an exception because soda doesn't exist. And then we have an exception happening while an exception was being handled. So they decided partially constructed objects just don't get destroyed. And then they, I guess, want you to be concerned about that as the programmer. So you need to know they don't get destroyed. So C++ only destroys fully constructed objects. There's no way to know how much of the destructor to run on a partially constructed object. So we would want the objects to either be fully constructed or not constructed at all. That would be great, so we don't want any partially constructed objects. So we could start doing something like this. We could say, let's try to create the popcorn, and if that goes poorly, well then nothing really got constructed. If we hit an exception here and bail out, there's really nothing to clean up. But if we construct one component, then we could say, all right, let's try to construct the second one. And if the second one goes badly, let's delete the first one and then rethrow the exception at the operating system. Right? Just basically, so now what our concern is, we want to make sure that we don't have any partially constructed objects. So each time we construct a part, that's great. Then we go to construct the next one. If anything goes wrong, clean up everything we've made before us. So we create the first object. If that blows up with an exception, nothing really got created, so there's nothing to worry about. If the first one works okay, try to create the second object, and if that goes bad, delete everything behind us, everything we created behind us. If the popcorn and the movie are created successfully, then try to create the soda. If the soda doesn't work, then delete the popcorn and delete the movie, and then continue the exception handling. Okay, so this idea kind of works, but then we're just going to have to keep doing this. If we had 20 steps, we're going to have, the thing's going to keep growing and growing. And the other thing is, the destructor would probably have very similar code to it. So we might even want to write the common code the constructor and the destructor would have, put it in one routine, and then have both of them call that routine. That might make it a little bit easier, but so now suppose sometimes when you're creating objects, the designer of the class would like the objects to be constant, the pointers to be constant. So that way, when it's created, we can pass the pointers around, and we know that people who are passing the pointers around can't alter. So let's say the movie, we don't want people to alter it, but we want people to be able to watch it. So if that was the case, constant pointers can only be initialized in an initialization list. They cannot be done in the constructor's body. So this is probably one of the hardest things to do when you start constructing objects, and we had constant pointers. We're now going to say the popcorn is a constant reference. We're going to get passed into us popcorn, movie, and soda information how to create these things. We'll get these passed in as references, and then we're going to say if the popcorn pointer is not null that was passed into us, then we're going to call new to make a new piece of popcorn, new movie, new soda. And then what we can do, so what's different here is this. Instead of the body of the constructor doing the work for us, we have an initialization list. An initialization list, remember, we can assign a value, an incoming value, to a variable before we start running the constructor. And then if we did that, we then don't have, the body of the constructor is not needed. And then we can make the auto pointers to those, we could use auto pointers to those types. So that way, if anything went wrong during this initialization, the auto pointer would guarantee that anything that was created will get destroyed. So it's just a convoluted way to get around the fact. More what I'm talking about tonight is not exception handling, but just now that this idea that exceptions happen, things go wrong. Yeah, in our try blocks we can protect the code that we wrote that's running, but sometimes while we're constructing something, things might go wrong. And there's a little bit different there because you can't put try and catch blocks in the constructor and have them, well, you know, we could put try and catch blocks in the constructor, which we had before, but if something went wrong, we can't count on the destructor picking up the problem, knowing where the problem, how far the problem got, so it wouldn't know where to pick up. So, okay, so now another issue is this. Suppose, this is something just to think about, and this was really a design issue for the language. Suppose while an exception is being handled, you're running some code, halfway through your code something unexpected happens, and an exception occurs, and now an exception handler is running. As the exception handling code is running, suppose another exception happens. Like the exception handler is trying to divide by 0, you know, does something unexpected. What do you think should happen then? What would you do then if you were designing, this is really now an operating system question, but if during the processing of an exception handler, another exception is thrown. So what choices are there? One would be ignore the second exception and just keep processing the first one. The other one might be abandon the first exception handler and just run the second exception handler. Any other choices you could think of?
Go first and then check the second after the first is done.
Continue finishing the first one.
Like, yeah, put it in like a stack or a play or something and finish the first one, then move on to the second one after the first one's finished.
Okay, so yeah, because whatever the issue was with the first one, we'd like to finish that one, but then we kind of run into that same issue.
But that was
where,
the one that threw the exception also.
Right, that one, something may have gone wrong, that one might not be able to finish. So if we dump the first one, should we then handle the second one? That is an independent set of code. So like, we used to say when an exception hit, we can't continue the code after the exception because whatever line went wrong during the exception, the following code might need it to have gone well. But now we're jumping to a totally different exception handler. Could we just stop running that one? Just abandon the first one and run the second one?
Well, is the second exception triggered by the first exception? The first exception needs the second exception. If the second exception is part of the first exception, then you need to handle the second exception so you can handle the first.
The second exception is handling the problem that the first one had. So
if the second one can recover, then you go on. If it's a mission critical system, definitely. Otherwise, it would probably just give up.
If the second one could clean up the problem of the first one and let the first one continue. Yeah, I guess
Is there that transparency between them? Because it's gonna
Well-
return a different object type.
Okay, so what I guess what you're saying is, suppose the software developer who wrote up the first exception, the exception handler that ran first, suppose that developer wrote the try and catch blocks really well, so that if an exception happened during that exception handler, the second exception would be able to handle it and the first one could continue where it left off. Then you could argue that we should let the second one run, and then whatever happens at the end of that, hopefully it returns the control back to the first one, and the first one can continue. So the operating system should allow it, but the operating system can't be guaranteed. Every programmer is a really good one and writes really good exception handling for their exception handlers. It might just turn into a disaster. And they have to just, decide which way to go. And I could see the argument could go both ways. You could say, let the second one run, hopefully it'll take you back to the first one and the first one can continue, but maybe it won't. And at the end of the second one, the problem that the first one was trying to handle may not have been solved. But the developer will see a response thinking it's been solved. So to avoid that confusion, they just have a rule of thumb that says they completely give up and then just terminate your program. So that's just an operating system design thing that we have to deal with. So what we never want to do is have an exception go off while we're handling an exception. While the operating system is in exception handling mode, we don't want to do anything to trigger another exception, because then we're just going to be totally cleaned out of the system. So one big piece of advice is don't throw exceptions in destructors. And basically the reason why we don't want to throw exceptions in destructors is because when an exception happens, some code runs to handle the block that you're currently in, and then any object created in that block will be destroyed, right? Because that block has now come to an end. Usually you have a try block, and then somewhere in the middle of the try block an exception occurred. You run to your catch block, something runs, and now you're at the bottom of your catch block, which is usually just a close paren. Maybe do some more processing, but usually the bulk of your block is done. When you hit the close paren, all the objects created in that try block are destroyed. So all the destructors start running. And you're still in exception handling mode. That's part of the exception handling, is to destroy all the objects that were created in that try block. If during one of your destructors is running, let's say you have 10 objects to destroy, if the second destructor throws an exception, the 8 objects after that won't be destroyed, because now you've thrown an exception during exception handling. So you might think, oh, you're destroying an object, and if something goes wrong, I'd like to throw an exception, that's fine, and it'll work fine as long as you're not in exception handling mode, but as soon as you're in exception handling mode, the first time your destructor throws an exception, all other objects after that won't be destroyed, and then you have a memory leak. Okay, and then just some other side facts on exceptions is the exception types. Okay, so as far as exception types are thrown, there is another rule about the objects being passed, and they put this rule in place, and they kind of put it in place with no exceptions. When an object is passed from who's ever creating it, who's ever throwing it, to the exception handling code, it always makes a copy of the object. So you know how sometimes if you're passing an object to something, you're passing a parameter in a function, and the caller, the object will go out of scope as soon as it's called, the receiver will receive nothing. So in order to avoid that from happening, there's a rule that says that whenever an object is thrown, an exception object is thrown to the stack, when the exception handler begins processing, it makes a copy of the object. Okay, so how does that affect us? So yeah, this copying happens even if the object is not in danger of going away. Like if it is a static variable or it's on the heap, it's not going to go away just because it was called. It's not going to go out of scope. They'll still make a copy of it. So does that make sense? What I'm saying is if you try to pass it by, if you receive it by reference, you're still going to get a local copy of it. You're not going to get the object that was passed into you. Okay. So that affects something like this. Suppose we had, so we're talking about the topic of throwing an object and, I'm sorry, throwing an exception object or throwing the one that was passed into you. So if we have some code above here that says try blah 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 and then an exception occurs and this thing catches it. Let's say we have a math error reference and I'll call the object ME. And then we do some processing and then when we're done we want to rethrow the object back to the operating system. If we compare that to catching an object of type math error, also called ME, and then we throw ME, what's the difference? Okay, suppose math error is a base class, and then there are other specific math errors that derive from it. Like let's say overflow math error, or an underflow math error, or divide by zero math error, different types of objects that derive from this. When we receive the object, we copy it based on the type of this object. So we get the static, we get the base components of it only. So inside this block, only the base components are available to us, unless we recast it. And then if we throw it, we'll throw it as whatever it was that came to us. If a divide by zero error came in, and this is a base class of divide by zero, we'll catch it. We can handle it, and then we throw it at the operating system. It will get an object of type divide by zero. But if we do this instead, if we say the object that comes in is of type math error, the base class, and so if a divide by zero object comes into this, and then if we rethrow the object that came into us, all we're doing is now throwing a math error. We're no longer throwing the divide by zero error. So if something below here or on a different stack catches a divide by zero, it will not catch this one, but it would catch it in this case. If this was coming in by reference and staying by reference, then these two examples would be the same. We would just be throwing the thing that came to us. But we're getting a copy of it, and then in this case we're throwing the object that came to us, and in this case we're throwing the actual copy that we made. The brand new object that we created, we're throwing that instead. So that's just something to keep in mind. And then one of the last things on exception handling. This was added to the compiler, but it's not really enforced very well. But if we have a function, let's say we have a particular function. We create a function, and maybe I should have put an empty body, but anyway, we create a function. This function could throw any kind of exception. We could define a function by saying this function, this would be gunk, throws, and then we could build a list of the things it throws. So we're saying this function only throws exceptions of type A and type B. And then we could say a function throws, we build our list and leave the list empty. That means this function never throws exceptions. That's really what we're saying when we say throw. And this is true in Java and C# too. The problem is in C++ is if we say a function, this would be junk, throws nothing, we're claiming that this throws nothing. But then we call this function, which could throw anything. Right? This won't have a compiler error. And we've now created a function that could throw anything, even though we're saying it throws nothing. We say the function throws nothing, but it calls other functions that do throw things. If we started throwing stuff in here, it will have a compiler error. But it's not going to say, the compiler's not going to say, well, I know that this thing can throw anything, so I'm going to not let it compile. This ends up compiling. So they kind of put this in. It's more, this throw thing is kind of, it's, you could almost think of it like a comment, but it's letting other developers know, my claim is I don't throw anything. But the truth of the matter is it could conceivably throw something. Okay, So those are just some things I wanted to be mindful of. Things that we wanted to be mindful of now that this idea of exceptions can happen. So some of the stuff we talked about tonight is just gonna happen no matter what. We just need to know it could happen and how to handle it. And so some of the techniques we could use too is like those auto pointers could point at something that is not, an auto pointer can point at something so that if you forget to delete the thing you pointed at, or if an exception occurs, something happens beyond your control and you can't delete the thing that's being pointed at, you can still have the thing deleted. But then, yeah, the downside of that is it will definitely delete whatever objects it's pointing at when it goes away. So you may not want that. So you don't want to always use auto pointers, but that could help prevent memory leaks. Okay. So yeah, that's what I just wanted to, I know we talked about exceptions before, I just wanted to give an idea of what's going on and what things are out there for us to look for.